Hi and welcome. So today we're going to be covering nodal analysis, and the question really is it the best circuit analysis technique? Certainly it's one of my favorites, one that I use all the time. I really appreciate it, and hopefully you guys will learn a lot today as we go through this. So the idea is that if we're going to work on a problem or a circuit that looks like this, what are the advantages and disadvantages of using nodals? One thing I'm going to cover, and certainly the approach that I do, and hopefully within 3 steps you should feel really comfortable in approaching nodal. So when you look at this, our goals are solving for currents of the resistors, solving for voltages across each resistor as well. And our goal is to do it again in hopefully 3 steps. A simple layout like this is quite convenient because you can see things a little more clearly. And the idea is that when we're looking at these problems is that you're given current sources, right? And you have here also resistors, as you can see here. And this is a nice little problem because it has essentially a 4 mesh type of problem that you can traditionally do, or you can go ahead and use nodal, which hopefully the approach seems a lot faster. So when you look at a problem like this within the 3 steps, the first one is nodal, means you want to identify the node. All right, and a node again is just nothing else but a junction point where your wires will all meet. Okay, so that's what you need to think about. And the way I like to think about it is that if I was to build this circuit by hand or in a lab, I would think of a node as where I would solder all of my connecting points to. All right, that's a simplified version of it, and with practice it gets much easier. So traditionally in some textbooks you'll see it highlighted in the green, how I have it here, and that would be a representation of what a node would be. So again, if you're starting off this problem, the first question is how many nodes do you see? So again, you should identify 2 main nodes and the ground node as well. Some textbooks don't include the ground, some do, but this is traditionally called a 2-node problem, and the third one being the ground. And to observe this, I love to redraw the problem in this form. And this form is pretty interesting because you can see everything a little more clearly. You put both of them on your screen together so you can see how they look like. And the idea again is that here is our node, right? But it makes, if I draw it in this form, remember a circuit or a wire is just a wire in itself. You don't have to draw it in this fashion. I like to visualize it this way because it makes it so much more convenient. Because now in this form, I can see where I would actually have these nodes or these junction points where I would literally connect or solder my circuit together. And the reference or my ground node would be this bottom piece over here where they all meet. Notice again over here, they all meet. And with here are the junctions here, which represents a node. So that's really the hard part, is to understand or get a sense for what a node is. Sometimes we overcomplicate it, we overanalyze what a node is. But again, it's nothing else but a junction. If you think of it as a water flow, if you're standing on a bridge, you're observing the flow direction of water, would be where a node would be. Some textbooks describe it that form. But again, let's not overly complicate things and just think about it that way. Okay, and again, I'll give you more advanced definitions as we go through the video series I'm putting together. Number 2 is determining the direction of where your current is flowing. The whole idea of nodal, again, is that you're supposed to determine directions of current entering or leaving a node. Okay, that's number 1. So when you look at this, you have 2 options. You could either say the current's entering a node to be a negative value. You could say a current leaving a node to be a positive, or you can do vice versa. You can say a current entering a node is positive, a current leaving a node is negative. Technically, it doesn't matter. It's whatever you find to be most convenient. This is the method that I primarily use probably 90+% of the time when I'm working on these problems. Okay. The next thing I do, and I'll go over this in very detail so you get the hang of it. And once you get the hang of it, we can do more advanced problems as time goes on. I also like to summarize. I call it N1 and N2. Call it whatever you want. I just call it that way so I can keep track when I'm trying to solve these problems. All right, so number 3, which is our final step here, is to write a node equation. And what does that mean again? We're trying to sum up all of the currents at a node, which means that we're technically doing Kirchoffs Current Law, which says that the sum of all currents entering and leaving a node will summize to be 0. Really, really important that you get a feel for those 3 steps. Okay, so if we're to try to approach this problem, the first thing we'll do, because we have 2 nodes, we anticipate to write 2 nodal equations. If I had 3 nodes, I'd write 3 nodal equations, etc., etc. So for the sake of this problem, we have two nodes. We're going to first approach node 1 or N1, and we're going to try to write an equations that summarize all of my currents entering and leaving a node to be equals to 0, also known as our Kirchoffs Current Law for that node. Important as well, I'm going to assume the current across resistors is always leaving a node and it's heading to ground. What does that mean in logical sense? Well, because here's the ground again. So if you imagine your home, if you look at your basement of your house or any place, you'll notice that there's always one port or one rod that connects all of your electrical components in your home to ground, literally to ground, right? I have one in my house, and hopefully you have one, or you can see one where you live or at your job. And the idea again is that current naturally wants to go towards that ground anyway. So that's why I try to do that. I try to have all of my currents going that direction. Doesn't technically matter, but what really matters is that you're being consistent, and I'll show you how important being consistent is. So here we are again, we're evaluating only one node, and that node here is N1. And recall from the other videos or from your textbook that the current flow, right, always goes across a resistor from positive side to negative, right? So that means that based on my drawing, the positive and negative here, that means that the current is going the ground direction, it's going this way. And here, I'm going to assume, right, the current's going from the positive, right, entering to my resistor and leaving the resistor. So it's going like this. That's my assumption with that. Okay, and again, there's some assumptions to made when you're working with nodal, and actually there's assumptions all over circuits, but as long as you're consistent, as you'll see with my approach, it should make sense. Okay, so again, I'm going to assume that my currents, anytime I see a resistor in nodal, and I'm not given the direction of that, I'm going to assume that the current across the resistor is leaving the node. Okay, it's really important. So leaving the node means that I'm expecting the current flow to go like this, with a resistor and a resistor always. The current sources, based on the arrows here, are telling me the direction of the current. So for example, here, this arrow is pointing upwards, which means the current's definitely going into the node. I know that with certainty because they're telling me that. Same over here. The current here is entering that because the arrow is pointing into that node, which is really important. Again, because of resistors, I do not know. I'm not giving that information, so I'm going to assume, it's a tough word to swallow in engineering, I'm going to assume that the current across those resistors is leaving that node, always. As long as you're consistent with that, you will always get the correct answer. Okay, so the next thing to do is to make an observation about your node. So here's my node, right? This little giant black ball. And I look at the branches that I have with my circuit for that particular node. So this junction, where I were to solder it, let's say, I'd have this branch here, another branch here, that's 2, a third branch here, which is 3, and a fourth branch here, which is 4. So my KCL equation, right, it's going to be 4 branches, 1, 2, 3, 4, all of them summing up to be equals to 0. Extremely critical. Okay, so here it is. I'm going to zoom out a little bit so you can see it a little more clearly. So I have here branch 1, branch 2, branch 3, and branch 4. Okay, and here in this next image, I identify all of them. So here's my first branch, which I'm calling branch number 1. My second branch, which over here, third, of course, and fourth. So that's how it looks like. Everything that's in pink is node 1, and all of those branches will net equals to 0. Very impactful and extremely important to get the hang of. Okay, so take a look at that, pause it here, write this one down. This is pretty important that you get a feel for it. And this is what I'm actually doing in my head every time I'm setting up these problems. And I'm actually thinking about my approach and how I'm going to tackle it. And this is exactly how I'm formalizing these ideas as I'm moving along. Okay, so now that we have that, we have to write down the currents for each of those branches. Okay, so how do we get the currents? Well, we're going to follow the rules that we mentioned before, right? And the rules I'm going to be using here is that the currents entering the node is going to equals to a negative value, And again, the currents leaving the node, they're going to equals to a positive value. Okay, super important. So let's do this one together. So if we start off with my number one branch, over here, this arrow's going into that node. So therefore, the value for the current is negative 200 milliamps. Okay, so think about that. The second one, which is also given, right? It's given. How do I know it's given? Because there's an arrow there. Sorry, let me zoom out a little bit. Can't see that well. So the current here, the arrow is pointing inwards. So it's entering my node. So that's also been given a value of minus, right? A negative 50 milliamps. Okay, so hopefully number one for branch one and branch two makes a lot of sense to us because the currents entering are given the value of negative. Okay, that's my direction that I'm using here. The third branch, which is this one over here, it's really important that you get that one. So let's do this one slowly. So the third branch, if I recall from how we started off this one here, this is my node 2 is on this side over here. So I'm going to draw that in purple on this side over here. So what happens is that with this particular branch, okay, I am evaluating node number 1. So I have an unknown voltage of that node. Okay, so at the end of the day, we're trying to solve for the voltage of that node. The voltage of that node, which is my voltage 1, node 1, is going to have a potential difference between that branch and node number 2, which is on this side. Okay, and all of that over R. So let me say that slowly. So what we're essentially doing is that we're doing voltage over resistance equals to current. And how do we know that again? Because we know that V equals to IR. So what is our potential difference is what we're trying to understand between the voltage on my node 1, right, which is what this V1 is, and I'm taking the difference, potential difference, which I'm subtracting it from the voltage of this unknown branch over here, this unknown node here, which we call V2, all over 40 ohms. This entire thing gives me back a current. All this is a current. Okay, it's really important that you start to get the feel for that. So again, finally on this fourth branch over here, I have a node here, and that node here is, we call it V1, is my unknown voltage. I'm going to subtract that from this end of my resistor, and that we know it's our ground, and our ground has a value which is 0 volts. So we're doing V1 minus 0 volts over R1, which in this case is 20 ohms, right? Gives us the current across that branch. All right, so let me say that slowly, and then I'm going to revisit this problem again as we go through this, and I'll say it a different way to make sure you're all on board. Okay, so what we end up having now is that when we simplify this problem, right, we can simplify it by just doing some algebraic work. So we're trying to put all of our V1s together and our V2s together, right? And I have my, for example, I have my minus 200 minus 50 milliamps. I move all these two to the right side of the equation, get back positive 250, right? I simplify V1 minus V2, and I get an equation that comes out to be this. Okay, so I have one equation and two unknowns. The unknowns that I don't know are our voltage of V1 and our voltage of V2. All right, this is how you get a simplified solution. Do not worry, let me go over this one more time so you can see this when we say it to you now using the second node. So if we look at the second node over here, and the second node, say that our node here has a voltage, right? So voltage. And the voltage is going to have a potential difference, right? So voltage is going to have a potential difference between a high and a low. So the high and low will mean the voltage here versus here, the voltage of this node versus the ground again, the voltage over here versus this voltage of this node here as well. So we're always looking at these potential differences. Therefore, we also have, right, a voltage that exists over here. I'm going to call this voltage. I'm going to call it voltage 1. I call this side over here voltage 2 for simplicity. So with this one over here, what's important again is that our currents that are entering the node are going to be negative, right? So if we look at this, so you see here that we have here a minus 200. This is number one. The current's entering that node, so it's going to be a negative. The current is leaving this node for branch number 2. It'll be here a positive 50. And because we are in node 2, and we're trying to determine the potential difference between this end and this end of this branch, right? Then it's going to be V2 minus V1. That's the potential difference of those two, divided by the 40 ohm resistor, and that gives me back current. And finally, for branch number 4, it's going to be the voltage of this, right? We'll call it V2, and I'm determining the potential difference between that and ground again. Why? Because the 30 ohms is connected to the ground. So it's going to be V2 minus 0 volts all over 30 ohms gives me back a current. Okay, so with some simplification here, I could simplify this problem, right? Moving over to minus 250 to 50, and I put my V2s together. I'm left with something easier, which gives me back the voltage, an equation that satisfies the secondary node. All right. So what does that mean? Is that to solve a problem like this, what we're going to do is that we're going to solve for these two equations, right? I have equation 1 that we solved for before and equation 2. And I'm going to notice that I have two equations and two unknowns. My unknowns, again, are the voltage of that first node and the voltage of the second node in both cases. All right, so for a little bit of algebra, or you can use a determinant to solve. You can quickly solve a problem like this and get back an actual value. So depending on what you feel comfortable with mathematically, and again, pause it here if you'd like to write down these numbers or screen grab it, so you can practice this on your own. But the idea is that now if I use this method of determinants, essentially what I'm doing is I'm cross multiplying these two, right? So I'm doing 0.05 timesing it by the 0.058, repeating, and then I'm subtracting it from the cross multiplication of these two over here, right? And again, it's called Cramer's rule, so please look that up, or I believe I have a video on that already, so you can take a look at that as well. And I get back a value for my determinant. And once I do that, then I now set up my matrices. And now to solve for V1, right? I'm going to take the 250 milliamps and the 150 milliamps. I'm going to put it into its place into my matrices. I'm going to leave the minus 0.25 and the positive 0.583 over here. I'm going to do what I did earlier before, which I'm going to go ahead and cross multiply and solve. So here we go. So if we go ahead and we cross multiply those two, what you should see here is that you can solve for your value of V1. So for V1 in this case, I was able to get a mathematical value to be 4.88 volts, right? And I repeat this process again if I would like to solve for V2. And now I'm going to take this matrices that I had before, and in its place to solve for V2, I now put my solution of 250 and the 150 milliamps into this column of my matrix. And I do what I did earlier, right? Cross multiply these two, subtract it from the cross multiplication of these two. Again, go over Cramer's rule to see how to solve this mathematically. It's more convenient and it's kind of fast. And you get back a value of V2 to be 4.6 repeating. All right, so what does this mean? Okay, so I have two values, and what does this actually wholeheartedly mean? Okay, so graphically and solution-wise, what this means is that the node itself, N1, has a value of 4.88 volts. The node 2 has a value of 4.66 volts. And what that's trying to state is that it's trying to explain to you that there's a potential difference between this node and ground for this branch and this branch, right? And it's also going to compare the voltage from this node here and this node over here as well. And that all leads us to help us determine how much current is going across each branch, which is highly important to what we're trying to do. So let's see that a little bit more detail. So here's the details of this entire thing, all right? So let me zoom in a little bit for you. So the idea again is that remember that we were trying to write KCL for each of those branches. And you can see the minus 200, minus 50, V1 minus V2, so potential, and why again is it that for the 40 ohms? Because for each branch, which means I connect from one side to the other side, the wire, this one wire here can be represented as a potential difference of the voltages over the resistance, which is V over R, right? It gives me the current. And the takeaway from all of this is that each one of these brackets is an actual current value of each branch. So if I wanted to know how much current is going through the 40 ohm resistor, right? So I'm going to take the 4.88, I'm going to subtract it from the 4.6 repeating all over 40 ohms. It tells me that the current that's going through that top branch is the 0.00 or 7 milliamps is going through that branch. Okay, and if I wanted to know how much current is going through the 30 ohm resistor, it's going to take the potential difference. Oh, sorry, I meant the 20 ohms over here. So I want to know the current going through the 20 ohm resistor. It's going to be the 4.88 volts, all divided by the 20 ohms. And I know that I'm going to have back the 0.244 amps is how much current is going through it. What's cool about all this is that we can now show Kirchoffs Current Law, which says if I take all these values, I do minus 200 milliamps, minus 50 milliamps, plus the 0.07 amps, plus the 0.224 amps, I get back a net of 0 equals to 0. So that means I did everything correctly, which is kind of cool. It's like our check to see this actually worked. And it shows that the net current is 0. So what does that actually mean practically? That means that our system is conserved, that all the currents entering and leaving that node must net to be 0. Pretty powerful and pretty interesting. So I intentionally put a harder problem on first, right, to give you the hang of this. And again, take a look at this. You can see how I do the same representation now, but for my secondary node. So for node number 2, here it is again, the minus 200 because I'm entering, plus 50 because I'm leaving. Again, let me see here. We changed this actually. Let me add one more thing here to make sure it's clear. So this should be positive, negative, and when I'm evaluating it from this side, right? So now I'm on node 2. Technically, this should be like this actually. Positive, negative in that world. Okay, so now what I'm left with, and again, this is how it looks like if we're representing it only from nodes 2 position. It would appear that I'm going to have this potential difference of V2, right? Here's my V2. Minus V1 is the potential difference of those two nodes, all over 40, and then V2 minus 0 over 30 is the current that's going through this branch. So I get back numerics, which is important. I get back 0.155 amps is how much current is going through this branch, right? And I can see for that the 40 ohm resistor, it's going to be that 4.6 repeating minus the 4.88 over 40. So I get back a negative value. All right, so now we have some things to panic about. So the question is what in the world does this minus sign really mean from a practical standpoint? Algebraically, it makes sense, right? We're going to sum these up and you essentially get back 0 equals to 0. So we did everything right, which is helpful. But let's see what that means in our next example, because I think the next example is way easier. So it gives us a chance to understand this positive and negative stuff a little more clearly. So here's hopefully a simpler problem. Again, I intentionally went the hard problem first to give you a sense for how tough this could be, but in reality, it's not so bad. And we're going to try this one more time. So for this example, first thing I have to ask you is how many nodes do you see? So take a brief minute to think about that. And if you were to look at this problem, right, and I put the values now, we're going to use 4K, 2K, 2K, 12 volts, and 9 volts. We actually have one node, right? One node that exists that's over here. And again, you also have the ground, of course. So again, depending on how you were taught or what book you're using, sometimes they use a ground, sometimes they don't, as far as nomenclature is concerned. But as far as it looks like, this is how it really realistically is. You just have one node, right? You don't have to call this ground every single time, but you just have a node. And now you have a node and your ground. Extremely important. And notice it's the same, I redrew it so you have a better sense of how it looked like practically. So if I was in an actual lab or building the circuit, this is how I would actually solder it together. If this is my junction, here would be my ground. Or if I was to wire this in a lab, this is precisely how it looks like in my head. Why is that so important? I will show you why in a moment. Right, so one node, which means that we're going to expect to have one equation, so which is really important. And we're comparing potential differences between the node and ground for this problem. Nodal, you're always comparing potential differences between 2 points. Again, for this problem is much easier. We're comparing the main node to ground. So let's see what that actually practically means. So here it is again. Here's that drawing. because we have 3 branches, branch 1, branch 2, and branch 3, I'm going to have 3 things which net equals to 0. Again, I'm comparing my top node to this ground, the reference node, right? And in order to do that, because I have this node, it makes sense to give it a name. I'm going to call it V1 because I'm trying to solve for that nodal voltage, which we don't know what it is yet, but we're going to call it V1 just for that sake. For that sake, call it VA for all I care, but V1 is more practical, I think. So now that we know that, right? How do we write those equations? So for the first node, right, which is, we start over here, our first branch, which is this branch over here. Remember what I said before, if we do not know, if we're not told the convention sign of our resistors, we make an assumption that those resistors are always the current flow is always going towards ground, right? So that means it's going to look like this, right? So this is how we're going to make that assumption. So because of that, this 4K, we're assuming it's consuming energy, because again, everything nets 0, which is wild if you think about it. So in other words, if I start off with this voltage here, V1, it's going to have a potential drop, right? Potential drop that's happening here. So what is that potential drop of this for as far as the voltage is concerned? Okay, it's going to be V1 minus the 12 volts. Okay, let's think about that. So we V1 minus 12 volts. This is eating through 12 volts. And then minus 0 is truly how this should be written for that branch. Branch 2 is a little bit more obvious, and I'll go over this one more time, is that it's going to be my unknown voltage, V1, and I'm going to be subtracting it from 0 volts, which is my ground reference node for this particular branch. All of that over 2K gives me my current, okay? And this one over here is going to be V1, right? My unknown minus 9 volts, right? Minus 0 for my ground, all over the 2 kilo ohms give me the current for that entire branch. Now, if this doesn't make sense yet, it will hopefully now when I draw it this way. So what did I do here? And this is to help us see this problem. I took each branch from here and I redrew it as a straight wire, right? I drew this wire and all 3. And let's start with the middle one because the middle one's really obvious. So the middle one here only has one resistor, which is the 2K, okay? And I call it A or 1, so I called it A here, but you can erase that and call that 1, or here, we put it here so it's a little more sense, just for sake of argument. I just did that so it's hopefully simplifies this. So why is this so important? Let's try this again. So I have here my voltage here, and I have my ground. So that's how that entire branch looks like. So the other branch, the left branch, I have my VA or my V1, and then I have my ground on this side, and between those two, I have my 4K ohm resistor, right? And my 12 volts here. So that's how this branch looks like. And finally, my third branch is going to be VA, which equals to V1. And here's my ground, and everything in between those two is my 2 kilo ohms and my 9 volts. Okay, so there's a potential drop there. So what in the world does this mean? So what we understand from Kirchoffs Voltage Law, remember, when you're entering a node, you're using Kirchoffs Current Law. When you're evaluating a branch, you can use Kirchoffs Voltage Law. Okay, so if we consider this from Kirchoffs Voltage Law standpoint, what this means is that all of my voltages on a branch will net equals to 0, which is pretty wild, or at least we hope it does. And then this is how it would look like. So KVL states that I have my VA or my V1, which is over here, right? And my 4 ohm resistor, I anticipate that it's going to be subtracting, right? The 4 ohms. I'm going to subtract the 12 volts, right? It's consuming those 12 volts, will all equals to 0. That's what KVL is trying to explain. This branch makes way more sense, so let's do this one slowly. So again, this one here, let's think about this. VA, right, is our V1, which is my top node, and my ground node is over here, okay? So I'm going to have here from Kirchoffs voltage law, I'm going to have VA minus the voltage of the 2 kilo ohm resistor must equals to 0. All right, so let's think about that for one brief moment. So what does that mean from a math standpoint? That means that VA minus V2 kilo ohms equals to 0. So that means that mathematically that VA, let me delete this. If I plus V of the 2K ohms here, right, and I do plus V of the 2K ohms, basically I'm balancing this equation, I can show you that VA must equals to V of the 2 kilo ohms resistor. Super important, right? Try to imagine that for a quick second and why that makes sense, right? So that means that the entire voltage of that branch must be equals to VA, or which equals to V1, right? Which equals to V of the 2 kilo ohms. It's really important. So what I'm saying again is that for this branch, okay, that we're going to have here, this VA, the V of the 4 ohms, we're going to subtract that. We're going to subtract the V of the 12 volts. It's also subtracting from that. Must equals to 0, which is pretty powerful. So keep that in mind while we're doing this. And what I'm trying to say again is that because this branch, the leftmost branch, the middle branch, and the far right branch, if you think about it, right? Let's go back to this picture. They are all in parallel to each other. Right? Super important. So what does that mean? Okay, that means that they all have the same voltage from here to here. So from here to here, they're all the same. Really, really important. That's the first thing you learn in the circuits, is that any branches that are in parallel, the voltages are the same. Okay, so what is VA, right? Or V1? Okay, and what is this nodal voltage trying to state from a practical standpoint? So I'm writing this all down to get, if you get a better sense. So what that means is that if I was to probe this, if I was to go into a lab, and I was to connect the red, right? Sorry, my handwriting gets worse as time goes on. But if I was to take the red prong of my voltmeter, right, and then I was to attach it over here, and over here I have the black lead here, and I clamp them down from the top of that node to the bottom of that node, I should get the same voltage on all 3 of those branches. Even if I connected it, say, right about here, right, I get the same value, right? So that's what the node voltage is saying. It's saying that from a practical standpoint, if I get my voltmeter out and I connected it from the top of the node, and I connected my red lead, and I connected my ground, or my black clamp to the bottom of that node, I should get the same voltage of all of those 3 parallel pieces. So node voltage is the net voltage of a branch. Okay, that's super, super important. So what we see here again is that we expect that the net voltage for this particular branch over here, right, VA is going to have to equals to V of the 2 kilo ohm resistor. That should make practical sense to us, which means that if I was to probe from the VA to V ground, red and black, and I use a voltmeter, whatever I get across that resistor must also be the voltage of that node. It seems trivial now, which I hope it does in a moment. And then if I look at this branch again, it should give me back the same voltage as this branch over here. And how is that possible? Well, let's look at this algebraically. So if we're to solve for VA over here, well, VA will equals to V of the 4 ohms plus 12 volts. It's pretty wild, isn't it? So this is what we should expect that solution to be. And same, if we looked at this branch over here as well, we should expect that VA is going to equals to V of the 2 kilo ohms plus the 9 volts. Okay, this is super important of that practical being of this. And hopefully this concept of node is no longer frightening. It should make sense to us. It's just nothing else but the net voltage from A to ground, or V1 to ground. It's all it's trying to state. And what we hopefully are trying to understand from a mathematical standpoint is that things are getting consumed, and from physics or thermo, you're losing energy through heat. So V of the 2 kilo ohms and the 4K are literally consuming energy, right? So you learn that from your physics explanations, okay? So that is the big picture, and that's why I know it's sometimes a little bit frightening, but once you say, wait a minute, it's really not that complicated. It's nothing else but that net voltage. Things are getting consumed. I just need to figure out what those things that are getting, what voltages are, for example, V across the 4 ohms, and what V across the 2K will be. And I can do that using math, right? And that's it. So let's not trouble ourselves and try to understand this a little more delicately now. So when we look at this, again, we have 3 branches. So I expect 3 pieces of my equation. I'm going to have my potential V1 minus the 12 volts minus 0 all over 4K gives me back a current value, right? And then this one's straightforward, V1 minus 0 over 2K. And by the way, I don't write the 0 at all. I'm just showing this from a practical standpoint and how this actually develops. And again, that's from a potential difference. As a side note, is that if this voltage here was written with a polarity of negative, positive 9 volts, okay, it will simply be written as VA minus negative 9 volts. Okay, that's how you read it. So you read it from the convention states that you start from here is my potential, and I enter in this positive and always for my resistors, right? So it's going to always be the positive. I mean, it's going to be subtracting. It's going to be subtracting a positive 2K. And over here, I'm subtracting from the first sign that I see. So you only read from the first sign that you see, and the first sign you see is how you always go from the top node towards ground. Okay, I'll say it one more time. So if I'm going from the top node to ground, I'm doing VA minus, and I see the positive terminal, so it means minus a positive 2K is technically how you read it. And same here, it'd be VA minus a positive 4K and VA minus a positive 12V. But this one, if I inverted it, just make sure you keep the mental note that it's minus a minus 9V. If I have that condition, just give me a heads up. That's where a lot of people make a mistake, that they neglect the sign convention, but it's actually really important. Anyway, going back to our problem, here it is. So then just doing some algebra, right? Again, hopefully this is starting to make sense. I'm just doing potential difference between each of my sources, my voltage sources here, over the resistor will tell me how much current I have for each one of my branches. With some simple algebra, again, I multiply both sides by 2 over 2. To simplify this, just doing some algebra techniques, right? Just choose whatever algebra technique you would like. But ultimately, I'm trying to simplify this. And what I end up getting back algebraically is that V1 equals to 6 volts, okay? So because V1 equals to 6 volts, let's look at the practical example again. So here's my node, here's my ground. I now know that this entire node, my V1 or my VA, let me also add the VA because I know it's going to drive some of you guys nuts, my explanation, but it's the top node here, it's 6 volts over here. So I know the 6 volts here. So let's look back what we did earlier, right? So now because of that, let's do the middle one first. That's a little bit more obvious. So because I know that this is 6 volts here, 6 minus 0, of course, is still 6. So 6 volts over 2K tells me how much current I will have in this particular part of the branch. Okay. And again, I like this example again, because I can try to do this whole thing here. So I expect I'm going to have VA, right, minus V of the 4 ohms minus the minus 12 volts, and I can solve for V of the 4 ohms, correct? So let's see that algebraically. So algebraically, what I'm doing now, I'm just putting in the 6 volts everywhere. For any time I have a value of VA, I'm putting in the number 6. So now I have 6 volts minus 12 volts, gives me back minus 6 volts over 4. 6 volts over the 2K, right, gives me the current again. The 6 volts minus the 9 volts minus 0 volts over 2K gives me the current. So again, simplification, this is how everything looks like. So I have my currents everywhere. 6 over 4, 6 over 2, minus 3 over 2. Because again, 6 minus 9, negative 9 volts. So I get currents for all of that. So what's really cool is now I know that I have minus 1.5 milliamps, positive 3 milliamps, and minus 1.5 milliamps, all equals to 0. Why again? The entire system is conserved, so all the currents that are entering or leaving those nodes must net 0. It's fundamentally extremely critical that you get a sense for that. And I'll make another video about nodal so you get even more of a hang of it, but this is a nice introduction to it. So let's look at this, what this means practically again. I'm going to copy and paste this just in case. So here is my node, right? Here's my cool node. I can draw my node in this form, right? If that helps you. And remember, these are my solutions to my currents for each of those branches: left branch, middle branch, right branch. There's no such thing as minus or positive current. They're always just a flow, so just a value. The positive and negative means the direction. So remember from earlier, I said that if you have a value of negative, that means that the current is entering my node. Okay, if I have a value of positive, so I have a positive 3 milliamps, that means that my current's leaving that node. Again, over far right, I have a value that's negative, then this current is going into the node. So here it is. Entering node is negative, leaving node is positive, right? So this is how it looks pictorially. So pause this, because this is huge. So what this is stating is that my arrow direction is going upwards. My arrow direction for the night is over here. It's going upwards. And in the middle node, it is going down. So important. So we could have also assumed that, because notice, here's the positive terminal, negative terminal. So it's more than likely the flow is going to go this way. Positives up here, the current in from circuits, we know that it's generally leaving the positive terminal, right? Based on convention, it's going upwards. So we could have assumed that, but take a look at that. I never make the assumption using these positive or negatives. I let the math dictate the solution for me. And this is a solution that we get, and then it confirms our gut instincts of how it should have played out anyway, right? But don't guess this. A lot of people who are working on circuits start guessing the direction. It's easy when it's a 3-branch, 2-loop, or a simple problem like this. But when it gets super complicated, don't make that guesswork. Let the map dictate the solution for you. And this is how it looks like current-wise by focus only on this node. I like to draw it in this form because this makes a lot more sense to me. I'm evaluating this node over here, the node over here, right? And in this form over here, this drawing of it makes the most sense of it. This is how I draw it. And from another standpoint, it's what KCL could also be explained as the sum of the currents entering equals to the sums of the currents leaving. So the sums of ins equals to the sums of the outs. So all of my currents entering or going in are the 1.5 and the 1.5. The 1.5, the 1.5, and the leaving is a 3 milliamps. Or I could write it in this form, right? And they net equals to 0, right? So it shows that I did my problem correctly. Algebraically, everything worked out, which is pretty exciting. So I get 0 equals to 0. 1.5, 1.5 minus 3 gives me 0. So it proves that the KCL worked for this particular problem. Okay, so here's a little more detail so you have a better sense for this. So the next thing to do is to ask yourself, well, what is the voltage of the 4K? What is the voltage of the 2K, right? Well, because we already know that the current is the same on an isolated branch, right? So if here's an isolated branch, means it starts here to here, right? That means that the current here is going to 1.5, here it's 1.5, here's 1.5, here's 1.5. So the entire branch is 1.5 milliamps. So I get back the voltage across the 4K must be 6 volts, okay? And again, for this right branch, it's 1.5 is what we solved for. So it's 1.5 here, 1.5 here, it's 1.5 everywhere on an isolated series portion of your branch. So here to here, it's series, okay? So it means it's 1.5 milliamps the entire way through. So because of that, 1.5 times it by 2 kilo ohms, 1.5 milliamps times by 2,000 ohms, gives me back 3 volts. So I get back the 3 volts going across that branch. Okay, so here is how it looks like algebraically. Okay, so graphically, sorry. So graphically, I have here, let me zoom. Okay, this is perfect. So now let's look at this together. So the current leaves this here. We solved algebraically the current's entering the node, right? And we said that the current always enters the positive terminal of a resistor, okay? So again, the current flow always enters the positive end. So the current's going like this into the node, okay? This way for the middle branch. And finally, this way for the right branch as I showed you earlier. Okay, so with this graphic over here, that means that it's going to look like this: minus, positive, positive, negative, minus, positive, minus, positive, positive, negative is my entire voltage. So let's go one step further. So remember, so now we're going to plug in our values that we're able to we're supposed to have. So if I know my voltage across VA, which is this top node over here, right? We solved that earlier. And let's say we didn't know that, by the way. And then now we know it's positive, negative. So in order to read this equation algebraically, you start from this top, and if I'm reading it from VA towards ground, what it looks like is I have a positive VA, then I'm subtracted from a negative 6 volts minus a potential consumption of 12 volts equals 0. So again, I proved that VA minus 6 volts must equals to 0, or VA equals to 6 volts. And again, if we knew the value of the V of the 2 ohms, right? The V of the 2 ohms is going to be VA minus a positive 6 volts. So I have VA minus a positive 6 volts equals to this. So I can show that VA equals to 6 volts for the middle branch. And finally, for the far right branch, we solve for this to be 3 volts. So it's a potential difference of VA minus V2 minus 9 volts, but it's read as if I'm reading it from VA towards ground, I'm reading it as I see it. So I'm going VA minus I'm entering to the negative terminal, so it's minus 3 volts, and then minus a positive 9 volts equals to 0. So therefore again, I get back VA algebraically equals to 6. So I just proved that all the voltages for all those 3 branches that are in parallel, all of them have a net voltage of 6 volts. And that is what the nodal voltage is. So node equals V1, which equals to 6 volts, which shows that all of these branches are all in parallel and they all have 6 volts net towards them all. So again, it's pretty cool. It's hopefully really useful that you see it this way. Hopefully doing the hard problem first was interesting. And now you see how we solve this, and we also proved KCL and KVL for each branch of this problem. And that is it. Nodal in a nutshell, right? And this is hopefully makes sense. Hopefully you're able to keep along. And I started with the tough problem first to go to the more difficult problem. If you did enjoy this video, kindly like it or subscribe. And I hope to see you again. Thank you for joining.